squared, which gets you some number which makes your life just a little bit better.
Oh.
So it'll be something. 1.14.
1.20375.
And that would be radians per kilosecond squared. Just realize that if for that problem you put down that as your answer, I know that you didn't do the actual problem because I changed most of the numbers.
I think they also gave you like a radial acceleration in the problem.
I gave you the formula for radial acceleration, for the angular acceleration.
Oh, I don't remember what I'm thinking. I might be thinking of a different problem.
You're on the second time, maybe you're looking at a test problem. You've seen the test already. Right. Questions about this lovely problem?
Ooh, that got twisted around.
That's 25.7, whatever, 16 out of 5.
So,
Was that where they was that, you guys got C from the 16 natural log of 5?
the 16 natural log of 5 was the 25.751.
That's right.
All right, what was the other?
Number 6 on Master System 12.
The identical bricks. All right, and I gave dimensions, but, all right. All right, so if I've got an edge of a table and I'm balancing an object, assuming that there's uniform distribution there, you know, that object should be smack dab in the middle. That's basically the balancing, just a little bit more that way. If the center of mass gets off the edge of the table, it's gonna tilt and fall. If it's too far this way, then it's not gonna fall at all, it's very stable. But for instance, if this were the table and I had a break there, it's not falling at all. But we're trying to figure out how far out we can go. So this is half the length. That's how far we can get out with one of them.
But then doesn't they like balance another one on top and then like,
All right, now if I have two bricks,
thinking ahead.
if this is just on the balance there, the only way that I put a second brick, on the first brick in this position is if it's sitting straight on top. But we can get a little bit further out, because I want the center of mass of the two bricks to be at the edge of the table.
Oh, I see what you're saying. Okay.
So the top brick, this is at the halfway point of the top brick, so that's half of L. But the question is, what is that?
What is what?
This distance from the edge of the table to basically this point right here.
Is it
Okay.
a quarter?
Well, let's find out.
Like the new center of mass?
Pardon?
The new center of mass?
One more time.
So there's a new center of mass when you put that second brick on there?
I'm still missing a word.
There's a
Center
new
of mass.
center of the mass.
Oh, yes, a new center of mass, yes.
Okay.
Does it say where the bottom brick is,
Anywhere you want.
or is it just it's anywhere?
It's anywhere, I mean, it's not, I don't state where the bottom brick is, you're trying to figure out where that bottom brick needs to be on the edge of the table.
Okay.
So it's a center of mass problem wherever we want, so why don't we just sort of pick that as our, this is x is equal to 0, you can pick a different point if you want. I know that the center of mass is just the sum of mass times the center of mass over the sum of all the masses. N is the number of objects I'm working with here.
Wait, so what does that say? M
M sub I. Yeah, because I've got two masses here, so this be M1 and M2.
M sub I X C M I.
Okay.
X, that's the Cm for center of mass of mass I.
Okay. Yeah.
So in this particular case here, this would be, well, I know the center of mass of each brick is halfway through the brick, so this would be, if that's x is equal to 0, this is equal to, the bricks are all the same, so mass times 1/2 plus mass times the distance from here to where that second one is. Just put x for right there. X. Over 2m.
Does that equal 0?
And, no, not 0. Let's see, so I know x from there to there. If I know, oh. Do something fancy here. So ultimately, I'm trying to figure this out. That's where the center of mass of the whole thing has to be here.
There's a formula for that one right there.
Right.
Like that's the formula you had given us a while ago for the center of mass?
There's a video and the text one. So. I've got a different way of doing it, so, but. Explaining the symmetry argument, that would be a quarter of the brick. But doing it this way. So that's Y. Oh. That's half the length there. This edge, so that's half the length there. That's half the length. That's half the length. That's half the length. So that would be 1. Okay. The mass is going to cancel out, and you're left with 3/2 divided by 2, which is 3/4. So this would be 3/4 of whatever the length is.
Is that the final answer?
Is that the final answer?
Yeah.
No,
No.
because you've got 4 bricks.
So, in theory, is this, I mean, we might not be able to use this for every scenario because all the bricks are like the same bricks, they have the same mass and the same dimensions. Can we use symmetry?
Yeah, there's multiple ways of approaching it.
Okay.
My approach is to try 1, then 2, figure out the pattern. With 4, you probably could just calculate it out, or if I gave you 10, then you would have to figure out the pattern somehow.
Right.
Looking it up is not really an option if it were a test or quiz.
You think that's how they figured out stairs? I bet this is how they figured out stairs.
That's possible.
They got to like brick 10 and they were like, we could could probably climb that.
Wait, they're like, wait, this is a pattern.
It sort of gets messed up though when a person, if, you know, I could get these stacked out and figure out how far out it goes, but as soon as somebody steps past the edge there, the whole thing's gonna fall over.
That's true.
And it's possible that they did that, say, oh, okay, there's one, that one's gone, so, let's try a different way again.
Stairs before they invented supports.
But
Loaded
that's the general
stairs.
approach. Is there a need to do more?
I could always ask questions tomorrow, right?
Yep.
Okay.
Other questions on master set? All right. So let's hit sort of Zach's. Adding here. Pardon?
Said me too, to be honest.
All right, so Zach and Carly Ann's strategy.
It'll buff, it'll be alright.
Hit no buff, yeah, certainly.
Remember, you're not trying to outrun the bear, just trying to outrun other people.
Yeah. Yeah.
I missed the analogy.
Yeah, what does that mean?
It's the joke of these two people were being chased by a bear, and one of them stops to put his shoes on, and the friend goes, "Why are you putting on your shoes? You can't outrun the bear." And he goes, "I don't have to outrun the bear, I just have to outrun you."
Spitting bars, man.
Wow.
All right, so knowing the work energy relationships, I've asked that on more than one test. The fact that the total work, which is the total force, dot dxrs, whatever you're using, is equal to the change in kinetic energy. The fact that the non-conservative work is equal to the total non-conservative force, dot dr, equal to change in energy. And the conservative work is equal to the total conservative force, dot dr, which equals negative delta U.
I think on the test, you should put a question where we all get it right, because it's like, what's the kinetic energy formula? And if anybody like gets it wrong, you have to banish them from the class.
That's actually a good idea.
Give them a zero.
Yeah, I think
I've done questions before at various points in my career where I thought, all right, here's a gift for everyone, and just that
Make the entire
feeling,
test a gift.
that dead feeling inside when someone misses it.
Not worth it.
At least I may give all hard problems. I go, well, of course they didn't get this. This was a really hard problem.
This guy. I love that mindset.
I like that logic.
That's
I like
awesome.
that logic. Cause then he can't say we're just like pathetic. He's like, no, they give it a good try.
They give it.
Good try. It was a pathetic attempt.
And even if they're all, even if it wasn't a very good all.
I'm trying to find the right balance between gift and challenge.
Yeah, I mean,
I'll hit it or not, we'll find out.
No biggie.
All right, so this is the work done on an object is equal to the change in kinetic energy of the object. So work done on the object, change in the energy of the object. If I ask what is the work done by an object, it's just the negative of the work done on the object. Newton's third law. So if I do 5 joules of work on an object,
the object does 5 joules of work. Or
Negative 5
yeah,
joules.
Negative 5 joules of work.
on me, yeah.
Wow.
So conceptually, that's it, and then conceptually, non-conservative work transfers energy between objects. Conservative work transfers form of energy within the object.
So, this might, so I know that U is potential and K is kinetic. What is E?
Total energy,
Oh,
total mechanical energy.
Total
It's-
mechanical.
It's just kinetic plus potential.
Okay.
Alright, so these two add up to that. So that plus that is that. Because I have two types of work, I've got conservative and non-conservative, so the total non-conservative, total conservative, just the total. I need to know only two of these things in order to be able to figure out the rest of them. Just because of the interdependency there. Without putting any context onto it, if I just said delta K is 5 joules and work conservative is negative 3 joules, what are the rest of them?
8.
So we got work total, work non-conservative, change in potential, and change in total.
Well, work conservative is negative 5 joules.
Wait, which, you said work which
Work conservative.
was given to you?
Yeah.
What's
so,
what's the top one? Is that changing U?
That's a K.
Oh,
So that means that delta U would be 3. Total
So-
would be 5.
Total would be 5.
Yeah.
yeah. Total work would be 5.
Non-conservative has to be 8.
Yeah. Non-conservative has, well, yeah.
8.
So it's
Delta
delta
U
U,
is 3.
No.
Positive 3.
Positive 3.
so this has to be 8.
Yeah, and then that has to
8
be
joules.
8.
8.
Oh my gosh! I finally. That makes sense. It only took what, 3 weeks.
As long as you're there at the end.
Relatable feeling.
Now, if we're talking about change in potential energy, what could cause a change in potential energy? Besides conservative work. Give me a physical example of something that would change potential energy.
Raising an object.
There we
If
go.
my pen was like sitting here and doing nothing, that's like storing potential energy. Like it has the potential to do work, and then like push it, and that's like.
Yeah. I mean, if that works for you, that's fine. I've never been particularly fond of that
I like that.
definition.
I like
Okay.
that idea.
That has confused me throughout my years of elementary school through middle school and even high school. It took this class to finally get a better definition of potential energy.
Oh, so it really doesn't? Because that's all I remembered from.
Isn't it just how high it is?
I mean, it's, gravitational potential energy is an indication of its location relative to the gravitational source.
It could also be like
So, in practical matters, it's how high it is, but if I told you that the change in energy is positive 3 joules, it could be an object moves up.
Yeah.
What else could cause a change of positive 3 joules?
Heat it up.
could be
That would change kinetic energy.
compressing a spring.
Yes, or stretching. Disturbing a spring away from equilibrium.
And that's like elastic and inelastic, I guess.
That elastic, that ideal elastic medium,
Okay.
ideal spring.
Yeah. Is that the only types of springs we'll be dealing with? Like ideal ones?
Yes, although we did an example where, in class, where it was not an ideal spring, and we came up with an effective mass for it. The total change in kinetic energy is 5 joules. What does that mean? What had to have happened? Besides 5 joules of total work was done.
Well, let's say it started at rest and it had no kinetic energy, then the final, when we measured it, it had 5 joules of energy.
Okay,
That-
or in general,
it was
it's
moving.
sped up.
Yeah.
It's better.
Yeah.
So if this had been negative, it slowed down.
Yeah.
If this had been negative, that means that it goes either, if it's gravitational potential we're talking about, then it goes closer to the source. And that's true whether it's we're talking the generalized formula or MGH. And then that's pretty much it. So if you're given a problem like this, and I said, give me a scenario, I would recommend choosing a mass of 1 kilogram, just to make life easier for you, but you be you.
What did we start with here?
These two things.
And kinetic energy can be anything, right?
5. Pardon?
Kinetic energy can be anything, right? Like somebody running,
Yeah, as long as there's mass and speed.
like you have a car going on a road.
Yeah.
Okay. Just double-
Down to what we talked about earlier, down to the atomic level as well.
Oh, that's true. So atoms got.
Yeah. When you take the average kinetic energy of all those atoms, you have an indication of temperature.
Oh, that's what we did earlier.
Yes.
How,
That makes sense.
can you explain how we got the non-conservative work?
I know that this is the negative of the change in potential energy. So if negative 3 joules of conservative work were done, then my potential energy changed by positive 3 joules.
Will these be given to us on a formula sheet like that, or will we have to just memorize them?
Probably gonna look something like that. So once we establish, I know the change in kinetic energy, I know the change in potential energy, so the total change in energy is just the sum of those two, 8. I know that non-conservative work is equal to the change in energy, so if that's 8, I know that's 8.
Oversized.
Or, the total work is 5 joules, the conservative work is negative 3 joules, I know that conservative work plus non-conservative work is equal to the total work. So I have mathematically, this was negative 3 plus the non-conservative work is equal to 5. And solve, you get 8.
Why is it negative? That's just some,
Like, that was given.
What is conceptually, what does a negative conservative work usually mean?
The object's moving away from the source. So lifting an object, the gravitational force is down, but it's moving upwards. So the force is opposite direction of movement, so that's negative work.
Oh, okay. So by saying negative 3 joules, you're saying